Imagine you're baking your absolute favorite chocolate chip cookies.
Oh, I love a good chocolate chip cookie.
Right. So you use the exact same recipe, the exact same ingredients, and the exact same oven every single day.
Okay, sounds pretty standard.
But somehow, on Monday, the cookies are perfectly golden. Then on Tuesday, they taste like, I don't know, a mouthful of salt. And by Wednesday, they are just rock hard.
I mean, I would think I was losing my mind.
Exactly. You'd think your kitchen was cursed.
Yeah.
But that maddening scenario isn't happening in a home bakery. It is currently plaguing a multi-billion-dollar global metal industry.
Yeah, it really is.
Factory workers are using identical raw materials to make magnesium, but the level of contamination in the final product fluctuates so wildly it acts like a random lottery.
A very, very expensive lottery.
Seriously. So, welcome to the Deep Dive Lab. Today we're uncovering why this unpredictable contamination happens and how a team of scientists solved a massive industrial headache, not by inventing some billion-dollar machine, but by examining a really annoying piece of factory grime.
It is honestly a brilliant piece of scientific detective work. But to really grasp it, you have to understand why magnesium is so vital to begin with.
Right, because it's everywhere, isn't it?
Oh, absolutely everywhere. It's basically a superhero metal. It has an incredible strength-to-weight ratio, it's highly reactive, and it's actually biodegradable.
Which is wild for a metal.
Right. But because of those properties, about 80% of the world's primary magnesium is made using this highly specific process called silicothermic reduction.
Okay, silicothermic reduction sounds like a dense textbook term, but it's basically just an extreme industrial bakery, right?
That is the perfect way to look at it, yeah.
So from what I understand, factories take these briquettes made of raw materials, specifically calcined, dolomite, ferrosilicon, and a fluoride catalyst.
Yep, those are the ingredients.
And they load them into a massive oven called a retort and heat it up to a scorching 1,250 degrees Celsius. And they do this all under a vacuum.
Exactly. The dolomite is your source material, the ferrosilicon strips away oxygen, and the fluoride catalyst, it lowers the temperature needed for the reaction to actually happen.
Got it. But why the vacuum?
While the vacuum lowers the boiling point of the metals, it also keeps oxygen out so the magnesium doesn't just combust the second it forms.
Oh, right, because it's super reactive.
Oh.
So under that intense heat and the vacuum, the solid rocks literally vaporize into a gas.
Yeah, it's wild to picture.
Then that pure magnesium gas floats down this long tube to a cooler zone where it crystallizes back into solid metal.
Yeah.
But, and here's the mystery, there is a huge flaw in this setup.
A massive flaw. The final magnesium is just constantly plagued by aluminum impurities, and the unpredictability of it is frankly baffling.
So baffling. Like, how bad are we talking?
Well, in a study published in the journal Nature Materials, researchers looked at production data from a leading magnesium plant back in 2022. And they found that within a single 24-hour period, the aluminum impurity levels could just randomly jump from a highly pure 21 parts per million, all the way up to 845 parts per million.
Wait, what? In one single day?
One day. That is a 32-fold difference for seemingly no obvious reason.
That is the crazy cookie lottery I was talking about. When your output is that chaotic, it has to just destroy your market credibility. I mean, buyers need consistency.
Absolutely. So initially people believed they could just, clean the metal afterward. Treat this symptom instead of the cause.
Which makes sense. Just wash it once it's out of the oven.
Right, but when you're washing liquid metal, it's incredibly difficult. They tried a process called flux refining.
How does that work?
You add specific chemicals to the molten magnesium to bind to the impurities and drag them down to the bottom of the vat as like a heavy sludge.
Okay, it sounds logical.
It does, but aluminum is remarkably stubborn. It just stays suspended in the liquid magnesium, so that sludge method barely removes any of it.
So what was the backup plan?
The main alternative was vacuum distillation, which works perfectly, but...
Okay, wait, I have to challenge this. If vacuum distillation is the industry standard and it works perfectly, why are we even doing a deep dive on a new method?
That's a fair question.
Like, why not just invest in cheaper solar or wind energy to make the distillation more affordable? Why reinvent the wheel here?
Because the problem isn't just the price of electricity, it's the thermodynamic limits of the process itself. Vacuum distillation essentially means taking the solid, already made magnesium and boiling it all over again.
Oh, wow. Boiling metal twice.
Yeah. And even with free electricity, doing that at extreme temperatures severely degrades your factory equipment over time.
That sounds like a nightmare for maintenance.
It is. Plus, the higher the purity you want, the harder it is to separate those last few atoms of aluminum. It becomes this massive energy sink. It ends up costing an extra $858 per ton.
Per ton?
Yeah. It's insanely expensive. It just doesn't scale economically at all.
So the factory managers are basically just staring at their ovens, knowing they're loading the exact same briquettes into the exact same heat every single day, and just wondering where on earth this lottery is coming from.
Exactly. And this is where the story gets really interesting.
Enter the heroes of our story, Dr. Ziwei Shan, Rui Zheng, and their colleagues at Xianjiatong University.
Right. And they realized that staring at the finished, contaminated metal was a dead end. They needed to look somewhere else.
They looked at the trash.
They really did. During this whole baking process, there's this troublesome, brownish, highly porous deposit that constantly builds up on the inner walls of the cooling retort.
Basically just nasty oven grime.
Total grime. And factory workers absolutely despise it because it builds up, it acts as an insulator, blocking heat transfer, and just ruins the oven's efficiency.
So the workers were probably just aggressively scrubbing it off and throwing it in the dumpster, right?
Exactly. Standard operating procedure was just scrub, toss, and start the next batch. But Dr. Shan's team treated that janitorial nuisance like a crime scene.
I love that. So they put this brown crust under an X-ray, and they found it wasn't just random dirt. It was a very specific, complex crystal.
Yeah, a really complex one.
The chemical signature was 12 parts calcium, 14 parts aluminum, 2 parts fluorine, and 32 parts oxygen.
Which is a mouthful. But the massive takeaway from that X-ray is that the annoying factory crust was just absolutely loaded with aluminum.
Right, which was the skeleton key to the whole mystery.
It completely blew the case wide open. It told them exactly what was happening inside that vapor cloud in the oven.
Because of the fluorite catalyst.
Yes. Remember that catalyst mixed into the raw briquettes, the thing supposed to help the process?
Yeah, it was supposed to lower the temperature.
Well, it turns out it was highly reactive with trace amounts of aluminum naturally hidden inside the raw rocks. The fluorite was actively turning that solid aluminum into a gas.
Aluminum gas, specifically aluminum monofluoride, right? AF.
Precisely.
So the aluminum isn't just melting down, it is actively hitching a ride in the air.
Exactly. It's an airborne contaminant. And this is where vapor pressure comes into play. Aluminum monofluoride and magnesium gas evaporate at almost the exact same temperature.
Oh no, so they're just inextricably linked in the vapor cloud.
They are floating down the tube side by side, which makes them impossible to separate just by, tweaking the thermostat a few degrees.
And that completely explains the chaotic lottery.
The
daily fluctuations weren't caused by the raw materials changing at all.
Not at all.
They were caused by completely natural, slight variations in the temperature of the oven's cooling zone. On some days, the internal weather of the oven favored the formation of that brown crust, which trapped the aluminum on the walls.
Right. And on other days?
On other days, the weather shifted, the crust didn't form, and all that toxic aluminum gas dumped straight into the final magnesium product.
Which is such a satisfying aha moment for the scientists. They finally understood the mechanism. The villain was sneaking in during the vapor phase.
But, okay, if the aluminum is hitching a ride as a gas, they can't just scrub it off the walls later. They need something to catch it while it's actively floating down the tube.
Right. They needed a trap. And their solution is honestly a masterclass in reverse engineering a natural accident.
Because they looked at the brown crystal on the wall and realized the calcium and oxygen were already acting like a natural chemical magnet for the aluminum gas.
Exactly. So they hypothesized, well, what if we intentionally build a filter inside the oven, instead of just hoping the crust forms accidentally?
Right. So they took this to the lab, they built a miniature retort, and they generated the magnesium vapor at the normal, scorching 1,250 degrees.
Yep. But directly in the path of the vapor flow, in a zone sitting around roughly 1,000 degrees, they placed chunks of solid calcium oxide.
So they essentially built a Brita filter out of calcium rocks, right in the middle of the gas flow.
Like an extreme industrial Brita filter, yeah. And the physical evidence was undeniable. When they opened the tube afterward, those pristine white calcium oxide chunks had turned brownish black.
Oh, wow. So you can physically see it working.
You could see it. They had sucked the aluminum gas right out of the air as it floated by.
And the numbers back it up, right? Like the magnesium from their control setup without the filter had an aluminum impurity level of about 109.5 parts per million.
Which is pretty high.
But with that simple rot filter, it plummeted to just 6.3 parts per million.
Yeah, that is a removal efficiency of over 90%.
That is just incredible. But, I have to play the skeptic here for a second.
Go for it.
A tiny lab tube is one thing. But what happens when you try to scale this up? If you try to put a giant rock filter in a factory making 30,000 tons of metal a year, won't you just physically block the pipeline?
That is the exact hurdle where most brilliant lab science completely fails in the real world.
Right. You mentioned the factory workers hated the original grime because it blocked the heat and ruined efficiency. So intentionally packing the pipe with rocks sounds like a terrible idea for yield.
It does sound counterintuitive, but the researchers anticipated this, and their industrial twist is it's brilliant. They didn't invent some fancy, complex synthetic membrane. They used calcined dolomite.
Wait, calcined dolomite, that's the exact same dirt-cheap raw material already sitting in massive piles outside the factory, isn't it?
Yes. It's literally one of the main ingredients they're already shoveling into the ovens.
Wow.
Calcined dolomite is naturally over 50% calcium oxide. So the researchers just took a relatively small amount, roughly 500 grams, and strategically placed it at the cooler end of the oven.
Okay, so just enough surface area to catch the gas, but not enough to choke the flow.
Exactly. And regarding your point about heat loss, this is the best part. By placing it at the cooler end of the tube, the rock filter actually acted as a thermal blanket.
A thermal blanket?
Yeah. Instead of letting radiant heat escape down the cold end of the pipe, the rocks physically blocked that thermal energy and reflected it right back into the reaction zone.
So it actually trapped the heat where they needed it most.
Right. So it ensured the raw briquettes reacted even more completely. They produced the exact same volume of metal, but with unprecedented purity.
That is so elegant. And the financial shockwave of this simple adjustment is staggering. Like, before the filter, literal 0% of this specific factory's magnesium hit the ultra-pure Mg99998 grade. 0%.
Which is painful for a business.
But with a cheap rock filter, 83% of their batches achieve that top-tier purity mark.
It completely shifts the economic paradigm. Think about the old vacuum distillation method. We said it cost an extra $858 per ton.
Right, which is brutal.
This new passive rock filter costs $33.94 per ton.
Like $33? That's a 96% cost reduction. It's practically free compared to the old way.
It is. And because that ultra-pure magnesium sells for such a massive premium, this method gives producers a pure profit boost of about $1,400 per ton.
That is just wild. So the factory's swimming in profit, the scientists get a huge breakthrough. But let's bring this back to you, the listener.
Always a good idea.
Because unless you are heavily invested in global metallurgy, you might be wondering, why do I care about ultra-pure magnesium? What are the real-world stakes here?
Well, if you have a smartphone in your pocket or a laptop on your desk right now, you are actively relying on this exact purification process.
Really? How so?
Our modern tech ecosystem depends on semiconductor-grade titanium, and to refine that titanium, manufacturers use magnesium.
Okay.
But the magnesium they use must have less than 50 parts per million of aluminum. If it has any more than that, those microscopic aluminum impurities alter the electrical conductivity of the titanium.
Oh, so it just ruins the semiconductor entirely.
Completely useless. The foundation of our digital infrastructure literally depends on keeping aluminum out of the supply chain.
That is terrifying and amazing.
Yeah.
And it's not just phones, right? This impacts the global energy grid.
Huge impact there. Think about nuclear reactors. Critical internal components in a reactor core are made from a metal called zirconium.
And let me guess, zirconium is refined using magnesium.
You guessed it. And if there is trace aluminum in that magnesium, it transfers directly into the zirconium parts.
Which seems bad inside a nuclear reactor.
Very bad. In high-temperature steam environments like a reactor core, even a microscopic trace of aluminum makes the zirconium brittle. It will rapidly corrode and eventually fail.
Yeah, brittle metal holding radioactive material is literally a catastrophic failure waiting to happen. So keeping it pure is a massive safety issue.
Absolutely. And it even impacts the human body directly,
Right,
the medical implants.
Yes. Surgeons are increasingly using biodegradable magnesium screws and plates to repair bone fractures.
Which sounds like sci-fi. The body just naturally absorbs the metal over time. It does. As the bone heals, the magnesium dissolves, which completely eliminates the need for a painful second surgery to remove the hardware.
But the body is basically a warm saltwater bath.
Exactly.
Yeah.
And when you introduce two different metals like magnesium and a trace impurity of aluminum into a saline environment, it creates this microscopic electrical current between them.
A galvanic reaction,
Mm.
which causes the metal to break down way faster than it's supposed to, right?
Way faster. Plus, aluminum is highly neurotoxic. You absolutely do not want it leaching into a patient's bloodstream.
No, definitely not.
The researchers actually highlighted a terrifying statistic. If the aluminum impurity in a medical implant jumps from just 28.5 parts per million to 81.5.
Which is a tiny jump compared to the factory's original lottery swings.
Right. But even with that tiny jump, the medical implant will corrode 3.5 times faster inside the human body.
Wow. So a bone screw engineered to hold your leg together for 6 months ends up dissolving in less than 2 months. The structural integrity vanishes, and your bone just fractures all over again.
Precisely. So this discovery by Dr. Shan's team isn't just about saving factories money. It is the invisible safeguard ensuring our electronics work reliably, our nuclear reactors operate safely, and our medical implants perform exactly as designed.
When you take a step back and view this entire journey, it really fundamentally changes how we think about problem solving.
It really does.
Like, we started with this wildly unpredictable multi-million-dollar contamination crisis, and it wasn't solved by brute forcing the material. They didn't build a bigger, hotter, more expensive machine to boil the metal twice.
No, they didn't force it at all.
They solved it by paying attention to the chemistry happening naturally on the dirty walls of the oven.
It's a true testament to the elegance of reverse engineering nature. By examining those natural deposits, looking exactly where the impurities organically wanted to settle, they designed an incredibly cheap, perfectly compatible solution.
Yeah, science isn't always about forcing a material to do what we want. Sometimes it's just about giving the material the exact right environment to clean itself.
Beautifully said.
Which leaves me with a really provocative thought for you to consider today. If a pile of cheap, everyday rocks can act as a highly targeted, passive chemical magnet to pull toxic aluminum out of an industrial gas cloud.
Right. What else could we do?
Exactly. Could we engineer similar low-tech rock filters for our other massive environmental crises? Like, could a specifically formulated pile of minerals sit inside global factory smokestacks and just passively pull carbon dioxide right out of the exhaust before it hits the atmosphere?
Oh, that's a fascinating idea.
Or could a passive crystalline net seamlessly pull microscopic plastics out of our municipal water supplies?
I mean, the precedent is there now.
It is. Sometimes the cheapest, most revolutionary solutions to our futuristic problems aren't complex machines. They're already sitting in the dirt, just waiting for someone curious enough to put them under an X-ray.
I couldn't agree more.
Thank you so much for joining us for this exploration in the Deep Dive Lab. Keep questioning the everyday world around you, and we will catch you next time.